let's talk about the memory consistency. Okay. So we've got 3 threads, all right, and each thread is only required to see the causally related operations in a consistent order, in a essentially sequentially consistent order. Okay. So thread 1 must see all the causally related events in the same order as thread 2 does, which must be the same as what thread 3 does. Okay. Thread 3 sees. And so what are the causally related events here? X equal to A is an event that happens before X equal to B. 2 writes, and a write is ordered after everything that happens before it. Then there is a write to X of the value C, which is thread 3. That also is causally related to the 2 reads before it. Okay, the 2 reads must happen before it. And there are the reads that are causally related. So thread 1's first read is causally related to the X equal to A write. Its second read is causally related to X equal to C write, right? And its third read is causally related with X equal to B, right? Okay. What else? And similarly on the thread 3, the read of X is related to X equal to A, and read of Y is related to Y equal to 0, and the read of X is related to just the previous write. Okay. These are all the causal orders, which must be seen by all the threads in the same order. Now, each thread really doesn't see other threads' reads directly. Right? Indirectly it might, but directly it doesn't see other threads' reads, which means that if you can ensure that other threads' writes are seen by the same order by every thread, then you have ensured that their reads will also be causally consistent. All right? Which means that we need to make sure that for thread 1, the writes, there are 3 writes, X equal to A, X equal to B, and X equal to C. And they are causally related with respect to each other through other reads. Okay? The first 2, X equal to A and X equal to B, are definitely directly causally related. But X equal to C is causally related through the read that is happening. And so X equal to A, X equal to B, and X equal to C must be seen in the same order by all the 3 threads. So what should that order be? Can you come up with that order? Okay. So if it is, so it's not just A, C, B, right? Order is also for a given thread, you have to place X equal to A somewhere, X equal to B somewhere, X equal to C somewhere. So you're saying A, C, B, right? So A has to come before C, but you have to place it somewhere. And so where does X equal to A come? In the beginning, read X, and the X equal to C comes before that, and X equal to B comes before that. Okay. What about the Y? Y is causally related to all the X reads because it's happening after, right? That means because the first thread says that all the 3 X writes have to happen before the last read, meaning that all the 3 X writes have to happen before the Y write. Y write.
X reads. But read write is causally related.
No. Y equal to 0 is the write we are talking about. And we are saying that all the other reads ensure that the writes to X must happen before the Y's write. Okay. So thread 1 says that the order should be x written to x a value of a, written to x a value of c, written to x a value of b, and written to y a value of 0. That's the order. Is that consistent everywhere? Thread 3 cannot be explained with that order, right? And so there is some causal relationship that is being violated for whatever reason. All right? Okay. Any other question?
So we do processor.
Processor, okay. What does processor consistency say? That writes of a given processor have to be in the same order everywhere, right? Meaning that x equal to a and x equal to b must be related consistently, okay? By itself, that means FIFO. Processor consistency on top of it says that all the writes to x, even if they're happening on a different thread, must be seen consistently. Right? So that means that x equal to a, b, and c must be seen consistently everywhere. And that order, first a, then c, then b, will explain all. Right? Writes to y is only in thread 1.
So ACB is not necessarily required here, right? It might be even ABC.
ACB.
Because then only from one processor should be consistent.
If it is ABC, then how will you explain what thread 1 saw?
But what it sees is thread 2 wrote x equal to A, then it wrote x equal to B. So
If it wrote x equal to b, then why is it reading x equal to c?
So, but according to the processor consistency rule, that the writes by one individual processor should be seen in the same sequence, right? By all processors. So
That's the FIFO part of it. There are two conditions, right? One says that writes by any processor, or let me say writes of a processor have to be seen consistently everywhere, okay, in the same order. And then it additionally says that if there is some write to a given variable, then that must also be seen consistently everywhere, okay? And so the variable thing ensures that x equal to a, b, and c must be seen consistently everywhere. But y equal to 0 appears only in thread 1, right? Which means it doesn't have to be ordered with respect to any other write of thread 1. It doesn't have to be ordered with respect to any other write at all, because there is no other write to y anywhere else. So y equal to 0 can be seen wherever by other threads, thread 1, 2, and 3, or thread 2 and 3. Okay, anything else? So we'll talk about message passing interface next, because primarily one reason is that is what your next assignment is going to be. And I was thinking, if you want to do this assignment in group, then that may not be such a bad idea. But group has to be no more than size of 2. Okay. The other in the feedbacks there wasn't that much of a feedback, but there was one person who said that let's not discuss MPI type stuff in class. We can learn that separately, which is true. You should learn that separately, and in fact I am not teaching you MPI in class because you shouldn't rely on all I say. But at the same time, the reason I am also spending a lecture or so on kind of the programming interfaces is not just to learn a specific programming interface, but to understand what programming interfaces entail. If you're designing a programming interface, what are the types of decisions you would be making or you would have to make, okay? And so, although you learn how it works in a manual, looking at it at a slightly higher level, which I hope you're getting some sense of in the class, is useful. Okay, so that's precisely why we are talking about MPI also. So OpenMP was shared memory model, and as far as you can give or some software layer can give that impression that I've got shared memory, whether or not all processors actually physically share a memory or not, that's an excellent programming model. There are others. There is Intel has a programming model that it has recently started advertising, so to speak. There is another thing called Silk, which is a bit more language-like than OpenMP. OpenMP is basically a macro level thing. But once you have seen OpenMP, you will understand all of them because they have very similar design decisions, very similar way of thinking about how to program a shared memory. And so just the details may be different. And so as long as you've seen one, you can pick up the others relatively easily. None of those are well designed for non-shared memory. Okay. There is software that will sit on top of computers that don't actually share memory and give you an interface to a shared memory. Right? So you can still declare variables which may not reside on that machine's computer but on some other machine's computer and access it. Typically, these have not been successful primarily because of performance issues. Okay? When the programmer doesn't know, so far, when you, in the context, let's say, of OpenMP, when you accessed a variable, if it was in cache, you'll get cache behavior. If it was in main memory, you'll get main memory behavior. The difference between two accesses to main memory would be insignificant. Okay? That's also because it was a uniform memory architecture. Right? We also talked about non-uniform memory architecture. And although Intel's of the day are moving towards non-uniform memory architecture, but as long as that non-uniform structure is still tightly bound, say across a bus or within a single computer, the differences aren't that high. But as soon as you say this is across a network on another machine, that latency to your main memory and to a different computer's main memory becomes significantly different. And as soon as that happens, a programmer typically wants to know about it. Programmer would want to ensure that if your variable can sit on the place where it is accessed, then that's where it should be. If a variable is on a remote machine from where it will take a long time to fetch it, to access it, to write to it, then you do that only for other reasons, because your program structure necessitates it, or at least you would want to know that consciously. You would want to do that consciously. The program would want to control that. And that has been one of the reasons that MPI has become much more successful than other competing methods on multiple computer platforms. Okay. There is another interface called PVM, and in fact, MPI, the Hadoop style programming, which is MapReduce, they're all in some ways a competitor to MPI style interface, except they're at a somewhat higher level. So you don't have to, you don't get full control over everything, but sometimes that's a good thing because you can program in a more abstract way. So we'll see, at least to some extent, what PVM and MapReduce look like. PVM seems to not be as popular anymore. When it came out, it was quite popular, primarily because its performance with respect to MPI has not kept up. But MapReduce seems to be upcoming. It's not quite mature yet, still developing, so I don't want to base assignments on that. But it's something that is worth knowing about, so we'll probably at the end of the class try to spend some time on it. Okay, so that all is leading to the fact that now we are not talking anymore about a distributed programming model per se. Okay, because MPI is not saying here is a function and I'm going to write for I equal to 0 to 10 or 0 to some other number, and like OpenMP, somebody will run it on 10 computers. I equal to 0 on this, I equal to 1 on that, I equal to 2 on that. You would like something of that sort from a programming interface, from a parallel programming interface. In MPI, you are responsible for doing it. Okay, so MPI is essentially, as the name says, message passing interface. It says, I'm going to abstract away the details of the underlying network. Right? An MPI works on Ethernet as well as on other things. Right? It can be sitting across the internet. It can be sitting across other kind of fabric. And so all of that is hidden from you. And you see a generic way of communicating to other computers that you are cooperating with in solving a problem. What would you have to do so that you only want to know that I've got these 10 people somewhere, potentially remote, trying to do these 10 things, and I know what everybody is trying to do. And then I'll either give an intermediate piece of data to somebody or accept an intermediate piece of data from somebody. Okay? An intermediate could be input-output as well. Right? My output can be given to somebody, somebody's output may be coming over here. You can do it, you have to do it in a processor sense because they're all different machines. So they will be running at least one processor on each machine, one process on each machine. It is possible in this context to have multiple processes run on one machine also. Just like in OpenMP context, we said you can run multiple threads per core. You can potentially run multiple processes per computer, but typically that wouldn't give you the best performance. Why is it different from threads? I'm asking that I had earlier said that you would want to run many threads per core, right? So that you can hide latencies, you can fill the idle periods. However, for a single machine, however many cores they may have, I am suggesting you run one process, one MPI process per machine.
They don't share the address, shared variables.
Processes don't share,
So when they context switch,
and so they're just independent address spaces, right? So you can run multiple processes, but they'll be like doing two independent things, and you would be communicating with them through the MPI or some similar interface. You wouldn't be communicating with a shared memory. So you would rather use an OpenMP style program inside each of these processes, so that now the process is made of many threads, such that they among themselves keep that process or that set of processors, set of cores busy.
Let's say one process is one machine. Same, their processes distributed, they communicate. Individual processes are set up.
Individual process may have set of threads. Right? So you can imagine, for example, running one process, one program, let's say, on each of the machines. That program is an OpenMP style program that you have written, and they communicate with other processes on other machines.
Won't really be OpenMP style, right? In the sense the threads will be running on the same machine itself. The threads that
Yes,
we create.
So it is visible to the programmer. Programmer knows that these threads and these threads are not the same group of threads. Right? These are just thread set A, thread set B, thread set D. Okay. Okay, so that's about the general structure of how you may have your computation units, tasks divided.
OpenMPI typically runs like a wrapper, right?
OpenMPI.
Yeah, MPI. These MPI implementations typically run like a wrapper, right?
What do you mean by run like a
One
wrapper?
way is to have a library of this MPI.
OpenMPI is a library.
So how do you execute an MPI program? It's like you have a compiled binary.
Yes.
And you dot slash or something like that.
Something like that. We'll come to that part also. So I'll give you some of the practical aspects so that you can get started. And I'll give you some of the design side of things also. Talking about the design side of things, we've been discussing essentially over the last lecture or lecture and a half, this process of design, right? Where I said many times, when you communicate, you synchronize. Because when I'm sending you data and you are receiving that data, and I have to know that you've received that data, then one of us is probably waiting. Right? It's very unlikely that we are going to get to that receive and send point at precisely the same time, do a quick exchange and move on. Right? And so when you are designing communication, you've got to be very careful about, do you actually want to say, connect to that fellow, do some data exchange, and then move on, or have some data exchange happen in the background, hide the latency again. Okay, so you've got to think about whether it should be synchronous, or it probably needs to support both methods. Sometimes you do need to know that that fellow has received the data, and only then I can move forward. At other times, you say, sometime in the future that receiver will receive, and maybe I want to know when that receive is completed. I don't need to wait for it to complete right now and stop everything else. Okay, and so that is the asynchronous style, where I say, go ahead, send this, and later on I'll come back and ask, is it done yet? So that if something depends on it, which probably is true, I will at that time determine what to do. Okay, so I think this is probably a point where we need to stop for just a few seconds and continue beyond that shortly. So I said that it is really about message passing, and MPI has many implementations. In reality, MPI is only a standard, right? A bunch of folks got together and said, this is what type of communication is required, should be done by cooperating processes which are trying to cooperate to solve a problem, to compute something. And then there are various implementations, of which the most active right now is this OpenMPI implementation, okay, which is what is going to be available on the machine that you're going to run. It is going to be able to not only say, here is one process and it is sending data to another process. Okay, it's also going to be able to do some more group communication and group synchronization. Right? It will allow you to do barrier across multiple processes. It will allow you to broadcast data. It will allow you to gather a piece of data from here, a piece of data from here, a piece of data from here, and collect all of it, since the opposite of which is scatter. It will allow you to reduce all the different processes, produce some result, and you reduce that into a single value, the kind of reduction we have seen in OpenMP also. So all those things are also attached to this interface because it is not only a message passing interface as the name suggests, because that's what TCP is also, but it is more for the context of parallel programming, okay? Which means that there is notion of tasks, there is a notion of starting and stopping tasks, there is notion of killing tasks, there is notion of saying how many tasks to run on different computers, there is notion of saying that this program is going to start on these 6 computers. You run it at one place and it automatically gets itself copied at 6 different computers. Okay, so those kinds of facilities come with it, and above all, it's portable, right? So it's Windows or Linux or Mac OS or some other. So OpenMP is ported on lots of different platforms. So it's going to work similarly. So you will see the same interface. You'll program the same way, but one machine that you're talking to may be Windows, another machine you may be talking to is Linux, and it's all just going to work fine.
Why can't we say that the OpenPI is just a network protocol?
Because it's a little more than just a network protocol, right? That's what I was trying to just elaborate on, that it is primarily a message passing thing, but it also has a richer synchronization primitive. It also has a higher level structure on the data that you're passing across. So it is, you can think of it as message passing, but it's really message passing plus plus. Okay. Okay, so let's start with how you would run it. You can compile your MPI code with GCC or C++ or whatever. But there is a wrapper called MPI C++ or MPI CC, which then doesn't need to be provided with all the paths. Just like in OpenMP, there was -f OpenMP to suggest that this program is going to use OpenMP and use all the flags, paths, etc. MPI CC is basically that. Okay, it knows where you have installed. MPI CC is set up with all the location information when it is compiled, and so it knows what is where on your platform. You basically have to see MPI C++ mycode.cpp. Okay, and that code presumably has some MPI things, and it's going to link in with the right set of libraries to produce the executable. To run, you can't simply run that code as you would on a single machine. That could have been possible, right? Because in your a.out, it's possible that the library would have inserted something to make sure that it automatically starts in multiple places, but it's less clean of a method. So there is an execution program that MPI comes with, and you say, instead of you're just typing the name of your program and pressing return, you say MPI run program return.
So it's a wrapper, right? It's a wrapper to just.
MPI run is actually an executable, which is going to create some daemon, which is going to run this program at multiple places and set up the connections so that they can talk to each other.
So if I am running MPI program on multiple machines and I want to see which particular process is getting executed. So first on all of these, some MPI run or something similar will execute it, which will in turn.
No, you execute MPI run on one machine.
No, but MPI run will have to execute something.
Something, yes.
Right?
Yes.
Which will then fork, it will do an exec for the.
Exec for your program. Exactly.
So after a while, I'll just see my ./a.out or whatever might be.
Running on all the machines. Yes. It takes arguments, right? For example, in this example, you're saying it says dash host, some name 1, name 2. It says run this program on 2 hosts, host 1 and host 2. Okay. In this case, you're not even running on the local machine necessarily. Right? Host 1 may be some other machine, host 2 may be some third machine, and you just say run this program on those 2 machines. Okay.
What will happen if multiple people are sitting on 2 machines, there are 2 machines, both of them, somebody on machine 1 says MPI run the same command and another person says MPI run the same thing.
A different process. Right?
There will be
There will be no
independent
conflict.
of each other.
Yeah, it's independent of each other.
Here, how do we handle the multi-core? You said you can programmatically.
That is inside your code, the code that is in this exec. Right? So it's in your exec. That can be an OpenMP style program.
Again, then OpenMP is taking care of the.
Yes, MPI is not directly,
On its own does not.
only if you run multiple processes on one machine. Right? You can say run this program twice on host 1. You can do that.
I mean to say, if I give minus host and
Then it will run once.
local host, both local hosts here,
Yeah, then it will run twice.
twice as in on different cores or not that.
That's OS's business. OS will, assuming that there is nothing else happening, will actually schedule it on 2 different cores. But this is not directly part of it.
So the binary needs to reside on all the machines, right?
The binary needs to be accessible on all the machines. So basically, MPI run will log you in remotely on all the machines, right? Which is a bit of a problem over here, which we'll talk about shortly. Because to log in, you need to provide a password. You need to SSH. So MPI knows that it can SSH to run remote shells. But you need to provide a password, which means if you're running on 5 machines, you need to provide 5 sets of passwords, because it's going to run once on each machine. Okay, and it gets very confused. It's not really designed to keep that consistent. And so, in order for you to run it on our department environment, you are going to use public key and private key pairs. Okay, which means you SSH will not ask you for the password. It will do authentication by looking at your SSH private files on the other machine and just execute that program on the other machine. That's not full story, because we run Kerberos, which doesn't let SSH run if you don't have Kerberos token. Which means if you're going to run it on our department machines, you're actually going to have to log into that machine in a different shell to obtain the token and then run MPI run, because now you have the token. It's going to be able to finish the public key, private key authentication and will be able to run your program.
Can't SSH on normal.
Sorry?
Normal machine, SSH is disabled.
Yes. So in fact, you can't do it on other machines that are sitting on the desktops.
So one thing is, if you are of IO, for example, all the IO is encrypted in this SSH tunnel, right? But isn't that an overhead?
There is an overhead. If you don't want to do IO through this. And as a matter of fact, if the remote locations read something from input, they're not going to get anything, because all the remote IO inputs are channeled through DevNull. So when you run your program with less than some file name, the entire file is going to be read by the main program if you're running it on that host. Okay, the outputs are produced, but that causes synchronization issues, meaning that output will have to be sent here, merge with other outputs that are happening here, and all the other outputs are being sent. And so all the outputs will appear. They will appear, but they will appear in some arbitrary order unless you have caused it.
Messages, all these messages will be through this through that SSH tunnel,
Yes.
which will be an overhead, right? Because you can if you are not using SSH, then if you are getting say 600 Mbps with SSH tunnel, you are not getting more than 500 Mbps.
Right. That's true.
So why to have such
So it-
devices in MPI, in open MPI?
The Open MPI that's not Open MPI's business, right? Open MPI, that is your local how you run the remote shell business, right? If you are allowing people to simply RSH something, then it's going to do RSH. Okay. On the machine that you are going to be running, which is called Sheshnag, as I think earlier pointed out, it doesn't allow RSH as of now. We can look at that, but department security rules say that probably RSH will not be used. But it is not using Kerberos authentication for SSH, meaning that if you set up your key properly, then you shouldn't actually have to log into 10 different machines before you run your program. Okay, so that's
If it is only data, you can simply spawn and separate telnet process on some higher port, right? And use telnet as your remote shell.
but telnet is not allowed. Telnet is off,
No, telnet.
except 25.
You can run telnet on as a normal user on any port greater than 1024, right?
1024, yes.
Yeah, so that will increase the performance if your processes are message like more and more towards its message passing.
That is true, but I don't believe MPI has that control to change the port. Right, so it's either going to do SSH or RSH, whatever the remote execution methods possibilities are. Only that it can do, because it doesn't have its own remote shell routines. Okay, so now let's get to MPI itself. Okay, first of all, because we know that we are n things cooperating to do something, we're going to have a logical addressing, right? We're going to simply say that you are 1, you are 2, just like in OpenMP we used to say, thread ID. We just need a similar thing. So we don't call it thread ID, we don't call it process ID, we just call it your ID. So if I am generating n processes wherever, maybe on n different machines, maybe on just one machine, maybe on 2, 3, whatever, some number of machines, then all those processes together form a group. Okay, and you can create your own subgroups and all that, so that there is that additional set of tools are provided. And then you get a rank in this group, whatever your rank may be. You can query, you can say, am I thread number 3? So here I can say, what is my rank? And you can query how many members are there in the group. So you can say, I am 5 of 7. Okay. So there is this notion of groups. There is also a notion of context, which we will not get too much into. Context can have multiple groups. In all likelihood, you're just going to have a single context. Group can have subgroups and so on. There is also a notion of a communicator. Right? It's essentially an abstraction. That's really the abstraction of the network. Okay. In fact, it's still on top of network, because you don't really necessarily always say communicate to somebody, because there are some higher level primitives also. But communicator says that this is the channel. so to speak, the channel on which we talk. That channel may allow you to connect or talk to one person. That channel may allow you to talk to all the people at the same time. Okay, so there is this notion of a channel that you build up. Call it a communicator. And there is a default communicator. You can create new communicators. There is a default communicator which is which goes by this constant MPI _ com _ world, which starts with a channel on which all the members of a group sit. Okay, so that's the default channel, so to speak. You can create your sub channels just like you can create subgroups. And for each channel there is a group, and that group becomes the context now of this communicator. Okay, so for every communicator you basically say, I am on this channel, I am number 3, I am number 4, I am number whatever. So communicator can be queried. The examples are listed in red over here. So you can say, ask for what the size of your communicator is. You can ask for what the rank is. And in this case, the first parameter is the communicator that we are talking about. So in this case, this is the channel, which is the global communicator. It includes everybody that the group started with. And then you can send it an in pointer, and it will return to you the number of people in this communicator, in this group, as well as your rank. Okay. Some bookkeeping. You have to call this function MPI init. If you don't, MPI gets very angry. Okay. If you don't call MPI finalize before you quit, again MPI gets angry. Okay. It's going to give you unpredictable behavior and usually crash. And in fact, because you can be creating processes online and you don't know whether you have earlier called MPI init, there is a query function that says, has MPI init been called? So you don't call it again. Okay, so you can query whether it has been initted. Okay, so this is in some sense MPI. Okay, there is a function called MPI send, and similarly there is another function called MPI receive, and those two together are the message passing side of MPI. Okay. There are variants, there are several variants to it, but those two are the main. Now I'm not going to repeat, this is OpenMPI now I'm talking about. Okay. The function names are OpenMPI, but all variants of MPI end up using exactly the same function names so that it is consistent for whichever you are using. Now there's also a C++ binding. So there's a class MPI which has a subclass called com, which has a method called send. Okay. So if you're interested in C++, then you can use the class version. Okay. It will take essentially the same parameters. This is the only time I'm going to show you the C++ variant of the function. We're just going to look at the C variants through the rest of the MPI talk. And this is MPI receive. So you can send something, right? There is a buffer that you're going to fill data in that you will be sending. You will send some number of elements in this buffer. So count says how many I'm sending, and this type, MPI data type, says what is the kind of thing I'm sending. So you can send 1000 ints, you can send 1000 bytes, you can send 1000 floats, you can send 1000 some other struct that you may have. So all of that is in terms of elements, units of elements. Okay. And there is the rank of the destination who you wanted to get to. And with every message you get to attach a tag, right? So that you can create several streams on this channel. So if you say this is essentially a type of message. You say, I'm sending you the message and this belongs to message type 379. And so the receiver can say, I'm only reading messages of type 379. Alternatively, receiver may say, I want to receive all messages, but I want to know what type I received. Some is 379, some is 378. So instead of embedding a message type in the message itself, you can send an additional piece of data that says, this is a command I'm sending you, this is a request I'm sending you, this is a control data that I'm sending you, I'm telling you something about stealing your load or something of that sort, right? So in generic elements, you send the data you want to send, and one tag which you can use to say, this is the kind of data I'm trying to send, so that it can be interpreted properly, if you're sending many types of data. Receive is just the opposite of it. Receive will also provide a buffer pointer. It will say that I am providing so much space, count. It will say that I'm wanting to receive so many elements of this type, and I'm trying to receive it from this source, rank of the source. Okay. It can say that I only want to receive control messages at the time, at this moment. So the tag is provided by the receiver. The communicator, which channel we are talking on, and MPI status is the return value, which says something about how many. So it doesn't necessarily have to be that you are reading 20, you wanted to read up to 20 things, and 20 things is what it was sent. Right? Sometimes you know precisely I'm sending 20, you are receiving 20. Sometimes that varies. And so status says something about it. Okay? Status has details about where the message came from, what was its tag, how many bytes, how many elements came, and so on and so forth. Okay? Why does it have to have tag or the source? Not to authenticate.
Select from which source.
No, so identical wouldn't have status at all. Send doesn't have status.
No, alternative, which one has sent?
Yes, because when it says I want to read from this source, it can only get data from that source. But it can say source is any source. Whoever wants to send to me, I can read. Your tag can be any tag. Whatever type of message, whoever wants to send, I can read. And I'm going to see what type it is, who it is from, and then take their necessary action. Okay? So when you use wildcards in your source and tag, then you need this information, what actually came. Okay?
So, in a way, what OpenMP is to POSIX threads, isn't the case MPI is to RPC?
So far. Okay. These things are essentially MPI to, well, in some ways you can think of it, even the ones that we are going to talk about, the synchronization mechanisms, you can think of it as RPC++ in some ways, because RPC doesn't have them, but it might have had them. Okay. And all of these variants are blocking, meaning that when you send, you are blocked until some guarantee has been made. It's not necessarily that you are blocked until receive has happened. You are blocked until maybe your data has been copied into some other buffer. It essentially is an indication, if you are making a blocking call and you return, that your command has been taken. It is going to get executed. Okay? You can go change your buffer if you like, you can go change your variables if you like, but your command is guaranteed to be executed as you wanted. Okay. We'll look at those various types, and then it will become a little bit more clear. This is just a repetition of all the parameters that we talked about, which is replicated for receive. And let's go through a very quick example. Wait, I think we are running out of time. Let me stop here.